Right, hello students. Yesterday we have completed up to bidentate ligands. Under classification up to bidentate ligands we have completed. Let us continue the same thing. Now we start with the tridentate ligands. Tridentate ligands. Nature of the ligands. Nature of the ligand and the structure of the ligand. Abbreviation used in the complex. So, nature of the ligand, structure of the ligand, abbreviation used in the complex. Let us start with the tridentate, tridentate negative, tridentate negative. Under tridentate negative, let us consider this is what imino-diacetate, 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 IDA. The charge is important over each ligand. It is what -2 charge. The structure of the ligand coming to be NH diastates CH2 C double bond O minus diastates imino diacetate. It is represented by what? IDA in the complex. We show this particular IDA by representing with what? IDA. This is what tridentate negative ligand. This is what imino-diacetate, IDA. Next, tridentate neutral, let us consider tridentate neutral ligand, tridentate neutral, diethylene triamine, diethylene triamine, diethylene triamine, diethylene triamine, diethylene triamine, see diethylenes, CH2 taken to NH, CH2 taken to ice, NH2 and NH2. This is dependent in the complex simply with diene. Diene stands for diethylene triamine. This is what tridentate. This is the first donor, second donor and third donor. In this, the first donor, second donor, third donor. Tridentate negative ligand, tridentate neutral ligand. So, one is what negative ligand, one is what neutral ligand. These two are the important ligands under tridentate. Next, let us see tetradentate negative ligands and tetradentate neutral ligand. Let us start again. Let us take a tetradentate. Tetradentate negative, tetradentate negative, tetradentate negative. Under this tetradentate negative, nitrilo triacetate, nitrilo triacetate, triacetate. This is having a charge of NTA -3. Over each ligand, the charge over each ligand is important. How it is abbreviated, what the name, structure and abbreviation, charge of the ligand is important. Under tetradentate nitrilo triacetate, the structure of this particular ligand is nitrogen linked to 3 acetate groups, CH2 C double bond O minus 1 and second one CH2 C double bond O second one and third one CH2 C double bond O minus. Like this, nitrilo triacetate, first donor, second donor, third donor and fourth donor, 4 donor atom. It is represented in the complex. It is what NTA, nitrilo triacetate. Only one important ligand and tetradentate negative, that is what NTA. Next, let us see the tetradentate neutral ligand. Tetradentate neutral. Tetradentate neutral ligand. Tetradentate neutral. It is triethylene tetramine. Look the board. Triethylene tetramine. Triethylene tetramine. triethylene tetramine, triethylene tetramine. So CH2 taken twice, first ethylene NH, second ethylene CH2 taken twice NH. I said triethylene, one more ethylene group CH2 taken twice, triethylene tetramine. 4 amine groups are there. This therefore it is triethylene tetramine. First donor, second donor, third donor, fourth donor, therefore it tetradentate neutral. It is represented in the complex as triene, triethylene tetramine, triethylene tetramine, tetradentate neutral ligand. So tridentate negative neutral, tetradentate negative neutral. These two are important under tetradentate ligands. One is NTE, the other one is what triene. Next let us see pentadentate negative ligand, pentadentate negative. Pentadentate negative, pentadentate negative ligand. It is ethylene diamine triacetate, ethylene diamine triacetate, ethylene diamine triacetate. It is EDTA, it is HEDTA -3, ethylene diamine triacetate. Now it is very big ligand, CH2, CH2N, linked to only 3 acetate groups, CH2, C double bond O, O minus, first one, CH2, C double bond O, O minus, and again N, where N is linked to one hydrogen atom, and the second one here, C double bond O, O minus. See, first donor, second donor, third donor, fourth donor, fifth donor. So it is what a pentadentate negative. It is ethylene diamine triacetate. It is repeated in the complex HEDTA, HEDTA. This is what a pentadentate negative. It is what HEDTA. It is only the one of the ligand, very important under pentadentate, you remember. Next let us see the last one, hexadentate negative ligand, hexadentate negative ligand. Hexadentate negative, hexadentate negative is more or less identical to pentadentate, but there will be what 4 acetate groups. The same ligand we are calling it as what, ethylene diamine, ethylene diamine, ethylene diamine tetraacetate, ethylene diamine tetraacetate, ethylene diamine tetraacetate. It is what 4 charges, EDTA -4. Each ligand, its name, charge, density. Charge is important over each ligand, should not compulsory, but the charge over each negative ligand. In the case of this particular EDTA, you are observing I written as what, -4, then 4 acetate groups are there. Therefore, one of the hydrogen I am removing it and adding that one more acetate group. Therefore, it is what you call ethylene diamine tetraacetate. This is what the tetraacetate. Total number of donor atoms, look at here, 1, 2, 3, 4, 5, 6. Therefore, it is what hexadentate. It is abbreviated in the complex as simply EDTA. It is what EDTA. It is very important. You have to practice and know the structure. It's very important. You have to practice this particular ligand and you have to remember what is the actual structure of this particular ligand. Many times this particular ligand is useful for in your practical chemistry and here and there. Therefore, practice well. Try to remember this is one of the biggest ligand and hexadentate ligand, EDTA, one of the famous ligand used for many practical purposes. Next, this is the classification I have given to you. Classification of ligand based on charge and density. This is the classification: monodentate, bidentate, tridentate, tetradentate, pentadentate and hexadentate, either neutral ligands or positive ligands or negative ligand, all the different types of ligands we have covered. This is the classification only based on what I said, charge and density. Look here, one more classification is there, the classification of ligand based on nature of bonding, nature of bonding. A particular ligand is actually bonded to the metal ion in a particular way. The way it is bonded to the metal ion, based on this, we are classifying the ligands into again different types. Let us see the next classification of ligand. Classification of ligands based on nature of bonding. Next classification. See, I am putting the heading here, classification of ligands based on nature of bonding. Classification of ligands based on nature of bonding. Classification of ligands based on nature of bonding. Based on nature of bonding. First one, let me introduce flexidentate ligands. Flexidentate ligands. Flexidentate ligands. Look here, some of the ligands which are actually polydentate, they may or may not use all the donor atoms in bonding. Consider, suppose you are taking the sulfato ligand, yes, it is actually bidentate ligand, but often it is using all the 2 donor atoms, but often it may not use all the 2 donor atoms. So it is acting as what bidentate and also as monodentate. Consider the next ligand. Suppose you are considering EDTA ligand, EDTA is actually hexadentate, but it may or may not use all the donor atoms in bonding. So it is acting as what hexadentate. According to the situation around the metal ion, it can act as hexadentate and pentadentate and also as what tetradentate. Like that, a particular ligand may or may not use all the donor atoms. Such ligand is said to be what flexidentate, flexibility in bonding. Therefore, such ligands are known as what flexidentate ligand. Generally, all the polydentate ligands are having such character, flexidenticity or flexidentate character. Consider, suppose the best example you can consider sulfato ligand, and you can consider what EDTA. These 2 ligands you can consider as what flexidentate. Not only these 2, almost all the polydentate ligands you can consider as what flexidentate. Sulfato ligand is actually bidentate. It can also act as what monodentate. EDTA is hexadentate. Can also act as pentadentate, tetradentate ligand. Let me give 1 or 2 examples in which sulfato can act as monodentate and also as what bidentate. Look at here, one of the complex I am writing on the board, CO, NH3 taken 5 times, consider it is what sulfato. This is, let me write plus. One more complex I am writing on the board, COEN taken twice, SO4 again plus 1. In the both of these particular complexes, CO is what with the +3 oxidation number. With +3 oxidation number, CO can form total of 6 bonds around it. The maximum coordination number of cobalt +2 ion coming to be 6. Once it is forming 6 bonds, you are clearly looking on the board. Already the 5 amines are there. CO is linked to what 5 amine groups. Only 1 bond is left over. Only 1 vacancy there. The sulfato ligand is bidentate, we agree, but the sulfato involves only 1 donor atom. It cannot involve 2 donor atom, because out of 6 bonds, the 5 bonds are occupied by amines. Remaining the next single bond, the bond is occupied by what only sulfato. But sulfato is the bidentate, it can involve only 1 donor atom. Look the board how I am writing the structure of this particular complex. Look at here. This is 5 amines I am writing. 5 positions are occupied by this particular amine ligands, 4 and 5. And one of the donor atom, only one of the site is occupied by sulfato ligand. See, sulfato even though bidentate, but it can involve in only 1 donor atom, acting as what monodentate. In the next complex I am showing you, see, the same sulfato ligand is actually acting as what bidentate. Look at here how I am writing the structure of this particular complex. See, same sulfato ligand, but as shown in one of the complex the monodentate. See, it's actually ethylene diamine. It is what NH2, CH2, CH2, NH2. 2 ethylene diamines occupying 4 sites. Now this particular again CH2 and CH2 NH2. You are clearly looking on the board. This particular 4 sites are occupied by ethylene diamines, 2 sites are left over. Yes, sulfate has to use 2 donor atoms and the same sulfate ligand acting as what bidentate. Look at here, sulfate acting as what here monodentate, same ligand acting as what bidentate. Such ligands which are involving all the donor atoms or less number of donor atoms, such ligands are known as what flexidentate ligands. So sulfate here monodentate and also bidentate. We can also show with EDTA. Yes, it often involving all the 6 donor atoms or it involving 5 donor atoms or 4 donor atoms. Such ligands what we call flexidentate ligands. These are the best examples under flexidentate character. Next, let us see what are chelate ligands. What are chelate ligands? Second type you see is chelate ligands. Chelate. Chelate ligands. All the polydentate ligands are considered what chelate ligands. If the density is 2 or more than 2, by involving all the donor atoms in bonding around the metal ion, they are forming rings. Such rings are known as what chelate rings. Ligands are known as what chelate ligand. Let us take simple examples like ethylene diamine only take. What to say? Ethylene diamine. Consider one more ligand, diene, let me say. Diene, ethylene diamine and again diene. You take simply one more ligand like C2O4 minus 2. This particular ethylene diamine ligand, what I said, polydentate ligands are having this particular chelate character, chelate ligand. Polydentate ligands are considered chelate ligands. This particular density is 2 or more than 2. By involving all the donor atoms, look at here ethylene diamine. It is actually a bidentate ligand, NH2 and again here NH2. It is actually involving the 2 donor atoms in bonding. Yes, you are looking on the board. It is actually forming a ring around the metal ion. Such ring is known as what? Chelate ring, and the ligand we call it what? Chelate ligand. Like this, ethylene diamine is a chelate ligand. Consider diene. Consider diene. It is carrying what? 3 donor atoms. Next, CH2 taken twice, NH2 and NH2. See, this is 3 donor atoms it is carrying. First donor, second donor, third donor. Then around the metal ion, you are getting what? 2 rings. This particular 2 rings what we call chelate rings. Ligand is what? Chelate ligand. Ethylene diamine and diene. Let me show overall. One again oxalato ligand. You know the structure of oxalato ligand. This is what? Oxalato ligand. This particular oxalato ligand is a bidentate you are looking on the board. Let us consider it is linked to what? Platinum, like this. Around platinum, it is forming a ring. No, this particular ring is what? Chelate ring. The ligand is what? Chelate ligand. So all the polydentate ligand we can consider as what? Chelate ligand. First one is flexidentate. Second one is what? Chelate ligand. Next, let us see bridging ligands. Next type, bridging ligands. Third type, bridging ligands. Bridging ligands. See, some of the ligands are acting as a bridge between the 2 metal atoms. Bridge between the 2 metal atoms. Such ligands we call them as what? Bridging ligand. The best example you can take OH minus ion acting as a bridge between 2 metal atoms. Look the board. It can easily link to 2 metal atoms like this, acting as a bridge. So some of the ligands capable of forming 2 sigma bonds with the 2 metal atoms acting as a bridge between the metal atoms. Such ligands we call them as what? Bridging ligand. Under this example you can take OH minus, Cl minus, F minus. So OH minus chloroligand, fluoroligand, and you can take Cn minus, you can take NO2 minus, and sulfato ligand can also act as what? Bridging ligand. In addition to this, you can take amido, NH2 minus, imido, NH minus 2. You can also take oxo, peroxo, superoxo. All these particular ligands can act as what? Bridging ligands. They are all capable of forming 2 sigma bonds with the 2 metal atoms acting as a bridge all the ligands we can consider what bridging ligands. So flexidentate, chelate ligands, and again bridging ligands. Next, fourth type of ligands we can take as what ambidentate ligand. Let me show what are ambidentate ligands. Fourth type of ligands, look at here, ambidentate ligands, ambidentate ligands. See, these ligands are actually carrying two donor atoms or two lone pair of electrons, but while in the formation of the complex only one donor atom is involving. Such ligands what we call ambidentate ligand, carrying two donor atoms, two lone pair of electrons, but while in the formation of complex only one donor atom is involved, not two donor atoms at a time. Such ligands are known as what ambidentate. Ambiguity in bonding, such ligands what we call ambidentate. The best example you can take is here NO2 minus, right? NO2 minus can link with metal in two ways, NO2, or it may be M is linked to what oxygen. Here the donor atom is N, here the donor atom is what O. This particular bonding we call nitro. The same thing we say nitrito, nitrito, same ligand, but the donor atom here is nitrogen, here it is what oxygen. Only one ligand, whether it is involving nitrogen atom or whether it is involving oxygen atom, ambiguity in bonding. Such ligands what to call ambidentate. The best example is what nitro. Or you can also take cyano ligand. Look at here, it involves as what MCN, or it can also involve MNC. What to call this one? Cyano. The same thing what you can call it is isocyano. Cyano, isocyano. Next ligand say SCN minus. It is again SCN and similarly MNCS. It is what we call thiocyanato. It is what isothiocyanato. First one is what nitro, cyano, and thiocyanato. These particular ligands. One more let me give thiosulfato ligand S2O3 minus 2. It is also linked to metal ion by involving two different donor atoms. Often it involves sulfur atom. Next it may involve oxygen atom. This we write as what MsO2 ESO. Next second MoSO2S. Like this, what I said, some of the ligands are carrying two donor atoms, but in the formation of the complex only one donor atom is involved, but not at a time two. Such ligands what we call ambidentate. Ambiguity in bonding. Here whether nitrogen is involving, oxygen involving, that is what ambiguity in bonding. Such ligands what we call ambidentate ligand. Flexidentate, chelate ligands. Next this particular bridging ligands, ambidentate ligands. Next type of ligand, let us see pi accepting ligands. These are again very important. Pi accepting ligands. Next to see the fifth type, let me say that pi accepting ligands. These are very important. Pi accepting, or we can consider these are acidic ligands. Pi accepting or acidic ligand. Pi accepting ligands or acidic ligand. Some of the ligands like C, carbonyl, nitrosyl, cyano, triphenylphosphane, you can consider bi-pi. Such ligands are actually capable of donating a pair of electron, result in the formation of a sigma bond. Again they are accepting a pair of electron, result in the formation of a pi bond. Look at here, suppose a model I am showing. First this particular ligand is donating a pair, result in the formation of what sigma bond. Again from the metal accepting a pair of electron, resulting in the formation of a pi bond. See how it is. First it is donating a pair of electron, resulting in the formation of a sigma. Again it is accepting a pair of electron, resulting in the formation of a pi bond. Such ligand what to call pi accepting or acidic ligand. Accepting a pair, forming a pi bond. Therefore this particular ligand what to call pi accepting ligand. Let me show by taking either of it. CO is the best example to explain this particular pi accepting nature. CO is the best example. You take now the same thing I am representing like this. Consider carbon monoxide. You might be knowing this particular carbon monoxide. In the case of carbon monoxide, Oxygen atom is carrying a pair of electron and carbon atom is also carrying a pair of electron. The pair of electron in the carbon atom is actually there in the sp hybrid orbital. Sp hybrid orbital of the carbon actually carrying a pair of electron. Now this particular electron pair is first donated to metal ion. Look the board, clearly I am writing on the board. This particular, it is donating a pair of electron to metal, resulting a sigma bond. Next, from the filled metal d orbital, it is again accepting a pair. To represent the filled metal d orbital, I am showing with the lines the filled orbital. To represent, I am writing like this. Imagine the filled orbital. This particular filled orbital again donating a pair of electron to this particular carbon, C, resulting in the formation of what? Pi bond. What to understand here? First donating a pair, forming a sigma, again accepting a pair, forming a pi. Such ligand what to call this particular pi accepting ligand. Donating a pair and again accepting a pair, resulting in the formation of pi bond, therefore pi accepting. Why we are calling these as acidic ligand? Yes, according to Lewis theory, whichever is accepting a pair of electron, that generally we call it as what? Acidic. Therefore, these are pi accepting ligands and again acidic ligands you can consider. Next type of ligands, the last one, let me say pi electron ligands. Pi electron ligands. The last one, say pi electron ligands. Sixth one, look at here what I am saying, pi electron ligands. Pi electron ligands. Pi electron ligands. Pi electron ligand. See, generally a ligand means it has to carry a lone pair of electron, but in some of the ligands they are not carrying any lone pair of electron, but they involve pi orbital electrons, form the complexes. Without carrying any lone pair, they are forming the complexes by involving only pi orbital electron. Such ligand we call them as what? Pi electron ligand. The best example under this, cyclopentadienyl anion. Cyclopentadienyl anion. Cyclopentadienyl anion, the best example. This we can represent that C5H5 minus. The structure you can write as what? This is cyclopentadienyl anion. This particular ligand you are looking not carrying any lone pair, but form complexes by involving pi orbital electron. The best example under we can take, benzene is also acting as what? Pi electron ligand. Yes, you know well, benzene is not carrying any lone pairs, but pi orbital electrons are there. Then you consider the simplest example you can take, ethylene. Yes, ethylene is not carrying any lone pairs, but pi orbital electrons are involved in bonding. Such a ligand what to call pi electron ligands. I said, take the next example, you can consider benzene. Benzene is the best example under this particular pi electron ligand. Ethylene also you can take, acetylene also you can consider, ethylene, acetylene. These are forming complexes. Most of the silver complexes, platinum and gold complexes in this particular ethylene and acetylene complexes are there. But in this you are clearly observing not carrying any charge, but form complexes, both of these involving only pi electrons. Therefore, these are known as what? Pi electron ligands. So, different types of ligands based on the nature of bonding, flexidentate, chelate ligands, bridging ligands, ambidentate ligands and pi accepting ligands. Next type what? Pi electron ligand. This is the classification of ligands based on nature of bonding of ligands. So, we have completed two types of classification of ligand based on density and charge, and this one what? Based on nature of bonding. But you should be thorough with all the ligands. Once you are thorough with the ligands only, next part of the complexes it will become easy. You should know compulsory ligand, name of the ligand, structure of the ligand, charge of the ligand, density. These things you should know. Once you are thorough with the ligand, then only it will become easy for you to understand the next part of the complex compounds. Right. So next let us see, first we have completed the ligands. Next term what we use generally in the complex compounds is, that is oxidation number. Oxidation number. Oxidation number is easy only when you are thorough with the different types of ligands what I have given to you. Next oxidation number. oxidation number. Number of charges over the metal ion in a complex, it may be negative or positive. Number of charges over the metal ion in a complex, either it may be positive or negative, we call it as what? Oxidation number. Let me write a complex here, simply well known to you. I am writing what? Potassium ferrocyanide only, a well known complex to you, potassium ferrocyanide. Potassium ferrocyanide. Consider the next one, and again potassium ferricyanide. Potassium ferricyanide, K3FeC and taken 6. These particular two complexes are given to you. Imagine how to say the oxidation number of this particular complex, particular metal ion in this particular complex. Now, by looking the complex, you see how many negative charges are there in the complex. Yes, there is the equation to calculate x plus y plus z equal to 0 equation, but we need not apply always applying a formula and again calculating the oxidation number. It will take some time. Therefore, by looking the complex, you should be in a position to say what the oxidation number of that particular metal ion in the complex, provided if you are thorough with the nature of the ligand and information about the ligand. Very simple way I teach you. See, first check it, how many negative charges are there in the complex. How many negative charges? Say it is 6 I know 6 charges are there. How many positive charges are there? Yes, 4 potassium ions are there, plus 4. Out of 6 charges, 4 are satisfied by what? Potassium, remaining 2 satisfied by what? Iron. Therefore, you can simply say the iron oxidation number is what? Plus 2. Easy way of calculation. You need not put a x plus y plus z equal to 0. You need not put a formula. By looking the complex, you should be in a position to see the oxidation number. Come to the next one. How many ligands are there here? Minus 6, right, plus 3. Out of 6 charges, 3 charges are satisfied by potassium ions, remaining 3 are satisfied by iron. Therefore, iron oxidation number coming to be what? Here, plus 3. Still you can apply x plus y plus z equal to 0. That will take some time, but if the need to go for a formula, by looking the formula, you can easily see the complex. This is the way to calculate. I will give just 5 or 6 complexes I will write on the board. Still I will explain how to do this particular calculation of oxidation number. Still I will write some more complexes. Look the board. Look here, Na3 TiCl6, one of the complex. Take any charged complex, I will give MnCO taken 5 times. Let me write a anionic complex. Let me write this is what vanadium O ACAC taken twice. I am writing ACAC taken twice. Let me write one more complex, CONH3 taken 4 times, Cl2 Cl you write, right. Next let me write one more complex, simply I am writing NiCN taken 4 times, minus 4. See what is the oxidation number of this particular complex. How to see by looking the complex the oxidation number, right. It is how many charges inside? Minus 6. How many charges outside? Plus 3. Titanium becomes what? Plus 3. For this you need not put a equation x plus y plus z equal to 0. You want to take the equation, by putting the equation also you can calculate. By looking the formula also you can easily say in this way. Now come to this. You know well, carbonyl ligand, neutral ligand. See entire this particular bracket we can consider what? Neutral. But over the complex a charge is there, minus charge. Yes, the minus charge is actually over the manganese. Therefore, its oxidation number coming to be what? Minus 1. Next you see VOAC taken twice there. Yes, I already given the classification of ligands. Now we consider O. O is nothing but oxo. It is what? Minus 2 charge. And each ACAC acetyl acetonate ligand, each is what? 1. So minus 2 charge and again minus 2. How many total charges? 4 charges. 4 negative charges. Vanadium will become simply plus 4 oxidation number. Easy way to calculate. Next here, CONH3 taken 4 times, Cl to Cl. Look at here in this particular complex, 3 chloride ions are there. 3 negative charges. Cobalt will become simply what? Plus 3. Like this, you can easily calculate the oxidation number without putting any formula. Here you see, you can easily say how many charges are there in this? 4 charges. Out of 4 charges, 4 charges are as such remaining. So 4 out of 4 charges are as such remaining. Therefore, oxidation number coming to be 0. You want to consider nickel as X you take, and how many charges? 4 into -1 equal to what? -4. Then X will be equal to 0. Either the way also you can calculate. Either by putting the formula or by looking the complex, you can easily say the oxidation number. This is the way to calculate oxidation number. Ligands, next oxidation number. Next concept coming to be coordination number. I will explain what is coordination number, how to identify the coordination number of a given complex. See next one, coordination number. Coordination number. So ligands, oxidation number. Next concept is what? Coordination number. See, suppose you are given two complexes. See, first one CO Cl6 -3, and second one is C CO En taken thrice +3, En taken thrice +3. So one is CO hexachloride, second one is what? Trace ethylene diamine complex. Now what is actually coordination number? What is the definition of coordination number? You can consider number of ligands in a complex. You can consider what? Coordination number. But some of the ligands are monodentate, some are bidentate, some are hexadentate. Therefore simply you cannot say number of ligands equal to coordination number. It is better to say the coordination number of total number of chemical bonds between the ligands and again metal ion. So now you see the case of COCl6, chloride ions are 6, chloride ions to this particular CO total number of chemical bonds coming to be what? 6. Therefore coordination number is what? 6. Here COEN taken thrice, but number of ligands are 3, but total number of chemical bonds formed is what? 6. Therefore coordination number is 6. Why 6 chemical bonds we are saying? Each ethylene diamine is what? Bidentate. Each is capable of forming 2 bonds. Therefore total 3 ligands, and each is forming 2 bonds. Therefore total is coming to what? 6. Like this, based on the number of chemical bonds only, you can easily say the coordination number. The total number of chemical bonds between the metal atom and donor atoms of all the ligands, we can call it as what? The coordination number. Let me write few more complexes. Suppose CO-EDTA, CO-EDTA minus, and let me write CO triene. I am writing triene. What type of triene and what is the number of donor atoms we should know. Here EDTA is what? Hexadentate. Coordination number coming to what? 6. Here triene is actually carrying 4 donor atoms. It is capable of forming what? 4 chemical bonds. Then it will be what? 4. Like this, the coordination number, we can say number of chemical bonds between the central metal ion and the donor atoms of all the ligands. Like this, we can easily say the coordination number. First ligands, oxidation number, coordination number. These 3 concepts should be thorough to understand next part of the complex compound. What are they? Ligands, their structure, name, density, charge. Second thing, oxidation number, and next one, this particular coordination number. These 3 concepts should be thorough, then only you can easily follow the next part of the complex compound. Next we enter into theories of complex compound. Theories of complex compounds. Right. Theories of complex compounds. Theories of complex compounds. Now let us take the first one, Werner's theory. Werner's theory of complex compounds. Werner's theory of complex compounds. Let's see what are the important postulates under this particular theory. Postulates under this particular theory. First one. See, in metal complexes, metal ions are exhibiting 2 types of valencies. 2 types of valencies. Let us say primary valency and secondary valency. Primary valency, let me say again secondary valency. See, in metal complexes, metal atoms are exhibiting 2 types of valencies, primary valency and again secondary valency. Look at here, this particular primary valency equal to oxidation number. Primary valency equal to oxidation number. This particular valence is what? Ionizable valency we can consider. Oxidation number, and again it is ionizable valency. It is ionizable valency. You can take it is what? Non-directional valency. It is non-directional valency. We can say it is satisfied by generally negative ligands only. Satisfied by negative ligands only. So primary valency equal to oxidation number ionizable valency and non-directional valency, it is satisfied by negative ligands only. Coming to the secondary valency. Secondary valency equal to coordination number. Secondary valency equal to coordination number. It is non-ionizable valency. Non-ionizable valency. It is directional valency we can consider. It is satisfied by the negative ligand and positive ligands even with what neutral ligand. So it is equal to coordination number. It is non-ionizable valency and again directional valency. It can be satisfied by negative ligands, positive ligands and also by neutral ligand. All the different types of ligands can satisfy the secondary valency. Coming to the second postulate to take. The ligands which are linked to the metal ion by secondary valencies are fixed at particular positions, giving rise to particular geometry for the metal complex. Look here, 6 ligands are there. These particular 6 ligands are actually arranged at particular positions around the metal ion. Arranged at the particular positions around the metal ion. This particular, the ligands which are linked to metal ion by secondary valencies, they are fixed at particular positions, giving rise to particular geometry for the metal complex. What you can understand by this, based on the coordination number, you can say the geometry. Suppose coordination number, let me say geometry of the complex. Coordination number and geometry. Coordination number 2, the geometry will be what? Linear. Coordination number 3, the geometry will be what? Trigonal planar, well known to you. Coordination number 4, geometry coming to be tetrahedral. Another choice is there, coordination number 4, the geometry coming to what? Square planar. And coordination number 5, you can say it is what? Trigonal bipyramid. Coordination number 6, you can take it is what? Octahedral. So in this way, based on the coordination number, we can say the geometry of that particular complex. Next, third postulate, let us see what is this one. Each metal cation according to its oxidation number or primary valency possess a fixed secondary valency or coordination number. Secondary valency or coordination number. So based on the primary valence of the metal ion, there will be a fixed secondary valency or coordination number. See, primary valency or oxidation number, either say primary valency or oxidation number. Primary valency or oxidation number, and here fixed secondary valency, or you can take it is coordination number. Primary valency and secondary valency and oxidation number, coordination number. Let us see. Suppose a metal ion is having oxidation number +2, its coordination number may be 4 or 6. Primary valency 2, secondary valency 4 or 6, and the primary valency is what? 3, then it is exhibiting a secondary valency of what? 6. But all the metal ions are not exhibiting the +3 oxidation state. Now if you come across this particular nickel, palladium and platinum, generally they exhibit this +2 oxidation number and +4 oxidation number, but not +3, generally they are not exhibiting. Therefore, what we can understand, this particular 3 metal ions, what 3 metal ions, either you consider nickel, palladium and platinum. Look at here, nickel, palladium and platinum. These 3 metal ions are not exhibiting +3 oxidation state. In this particular +2, this is what generally exhibiting 4 and 6, but in the +4, the same thing, nickel +4 and palladium +4 and platinum +4 you take. These 3 metal ions in their +2 oxidation state, they are exhibiting 4 and 6, but in their +4 oxidation number, they exhibit only 6 coordination number. Like this, for a fixed primary valency or oxidation number, there will be fixed secondary valency or coordination number. Last postulate, how to write the structure of a complex according to Werner theory. So first postulate, second one, third one, fourth I am showing Sriti, the fourth postulate. What is the fourth postulate of Werner theory? Fourth one. While writing the structure of a metal complex, the ligands which are linked by the primary valencies shown by dotted lines and the ligands which are linked by secondary valency is shown by a solid line. See, if I write on the board, you can easily follow what is this particular. I am writing a complex like CO6 NH3 Cl3 NH3 Cl3. Look this particular complex. In this particular complex, what is the cobalt oxidation number? Cobalt oxidation number is 3 plus 3. Plus 3 means what is the primary valence of cobalt? It is 3. That means this particular 3 chloride ligands are bonded by what? Primary valencies. This particular 3 chloride ligand you have to show by what? Dotted line. Look at here this particular complex 6. If the primary valency is what? 3 and coordination number should be what? 6. Therefore, you are writing this particular complex 6 amine ligands are there, 6 amine ligands, and 3 ligands are what? This particular primary valencies. Primary valency I am showing by what? Dotted lines. You see chloro ligand, first one, second one, third one. These are what? Primary valencies shown by dotted line. Secondary valencies you have to show by solid lines. These are what? Representing the secondary valencies. Secondary valencies. First complex. Next you take, let me write another complex, second complex I am writing on the board. See, second complex CO 5NH3 and Cl3. Cl3. In this particular cobalt oxidation number coming to be same. What is the oxidation number? Plus 3 only. Primary valence is 3, but secondary valence should be 6. But how many amines are there? Only 5 amines are there, but you require 6th. 6 ligands you require 6 coordination number. Therefore, one of the chloride ligand satisfying both primary and secondary. Once the ligand satisfying both primary and secondary, such a ligand is shown by thick line, that is called solid line, and also by dotted line. That particular ligand which is satisfying both primary and secondary valencies, that is shown by solid line and also dotted line. Such ligand is said to be exhibiting dual character. In this particular I am showing on the board, see CO. This one of the ligand is actually satisfying both primary and secondary. I am showing by what? Solid line and dotted line. And remaining ligands only this what 5 amines I am writing, which are satisfying only secondary valencies. Secondary valencies. These are satisfying secondary valencies. Remaining 2 chlorides are satisfying only primary valency. The primary valencies are only shown by dotted line. These 2 are satisfying primary valencies, and 5 amines are satisfying secondary valencies, and one of the ligand is satisfying primary and secondary. Such ligand is shown by dotted line and solid line. The ligand which is satisfying this particular primary and secondary, that is shown by dotted line and solid line, that is actually said to be a dual ligand. In this particular complex, one ligand is what? Dual ligand. One is dual ligand. Here there is no dual ligand, but here one is the dual ligand. 2 more complexes are right on the board. Then you can understand what is the duality, how you are writing one dual ligand. In the next 2 complexes I write, I will show how it is, how the duality of a ligand you can understand. See, the third complex I am showing, this particular third ligand, third complex is CO 4NH3 Cl3. Look at this particular complex. Cobalt oxidation number is plus 3 and primary valence is 3. If primary valence is 3, secondary valence is 6, well known to us. In this, 4 ligands or amine ligands are there. Then you require actually oxidation number is plus 3, primary valence is 3, secondary valence should be 6. Only 4 amines are there. And remaining 2 ligands have to satisfy both primary and secondary. See how I am writing the complex, this particular. The 2 ligands have to satisfy both primary and secondary. Therefore, these are shown by dotted line and solid line. This is what the chloro ligand and chloro ligand. One of the ligand is only satisfying this particular primary valency. Right, remaining I am writing 4 amines. See here no dual ligand, here one dual ligand, here 2 ligands are actually dual ligand. The last example I am giving, see the fourth complex I am writing CO 3NH3, CO3NH3 and Cl3. In this particular also, cobalt oxidation number is 3 and primary valency 3, secondary valence should be 6. But what this 3 ligands have to satisfy both primary and secondary. This particular complex I am writing like this, see, first ligand, second ligand, third ligand. This particular 3 ligands are written by solid line and dotted line. Here 1 dual ligand, here 2 dual ligands, here 3 dual ligands. Like this, according to Werner theory, whichever is actually satisfying primary, that is shown by dotted line, and which is actually satisfying the secondary valency shown by solid line. But often a ligand may be satisfying primary and secondary, that is shown by solid line and dotted line, that is said to be dual ligand. There is no dual ligand, 1 dual ligand, 2 dual ligands and 3 dual ligand. This is about the different postulates of Werner's theory. Let us see what are the applications of what are the merits of Werner's theory. Let us discuss merits of Werner's theory. Merits of the theory, merits. So, whenever a complex is dissolved in aqueous solvent like water, consider this particular a Werner complex to take CO6NH3Cl3, a particular complex is dissolved in aqueous solvent like water. Suppose you are putting this particular into water. What number of total particles produced? Total number of particles. Total number of particles, number of chloride ions, how many chloride ions are produced, and what are the number of charges, and what is its electrical conductivity. We can easily understand from this particular theory. Once a complex is dissolved in water, what number of total particles are produced, what number of chloride ions are produced, and what number of charges are produced. Once you know these things, you can easily say whether it is actually conducting more electricity or less electricity, the best electrical conductor or poor electrical conductor. You can easily understand. Now this particular Werner theory much more based on cobalt and platinum complexes. He has actually researched with most of the cobalt complexes and platinum complexes. Let us take in a tabular form. I will take different types of cobalt complexes. Let us see from each complex how many total number of particles and total number of chloride ions and total number of charges, whether it is having lower or higher electrical conductivity in a tabular form. Let me explain. Concentrate more on this particular table. It's very simplest theory, but every time in almost all the entrance exams, 1 or 2 questions appearing on this Werner's theory. It is simple, but you can easily answer in the examination. Now Werner's formula. Werner's formula and modern formula. Werner formula and modern formula. Type of electrolyte. Werner formula, consider modern formula, type of electrolyte and number of chloride ions, number of Cl minus ions, number of chloride ions. Let me write one more column, number of charges. For each complex, let us see what is the Werner formula, what is the modern formula, what is the type of electrolyte, number of chloride ions produced, what are the charges. See, in the beginning Werner has given this particular formula for a complex, this is what we call Werner formula. But nowadays we are writing this particular complex by writing a coordination sphere, a bracket and all. But at the beginning he has given this type of formula for a complex. The same thing, look at here, cobalt, oxidation number is what? +3. When +3 is the oxidation number, coordination number coming to be what? 6. Coordination number 6. Therefore, whatever the ligands are linked by the coordination number, this particular CO, NH3 taken 6 Cl3. This is the Werner formula. This is what modern formula. Now, how many total charges? Total, what is the type of electrolyte? What is the type of electrolyte? The type of electrolyte you can say, see, this you are putting into water, you are getting a complex ion and 3 Cl minus ion. Complex ion and 3 Cl minus ions you are getting. So, one is the complex 3 Cl minus ions, what you can consider it as 1:3 complex. 1:3 complex, 1 cation, 3 anions, it is what 1:3. Then total number of chlorions. Number of chlorions produced for actually here 3 Cl minus ions produced, then you are getting 3 AgCl precipitate you are getting. So, modern formula, Werner formula, modern formula, type of electrolyte and number of chlorions, number of charges. See how many charges, 3 minus and 3 plus, total number of charges coming to be 6, coming to be 6. Like this, for each complex, the modern formula, type of electrolyte, number of chlorions and a number of charges you can easily see. Let me take one more complex and cobalt complex, the other 3 types of complex I write on the board. Now CO, 5NH3 Cl3. Again you see oxidation number plus 3, coordination number is what 6, but only 5 amines are there. Therefore, one of the chloride you have to write within the bracket, inside the bracket you have to write CO, NH3 taken 5 times, NH3 taken 5 times, Cl and again Cl2. Look here. Type of electrolyte, 1 cation, 2 anions, therefore it is what 1:2 complex. Number of chlorions produced, 3 chlorions here and 2 chlorions, then we can say 2 Cl minus and 2 AgCl precipitate you are getting. See next how many charges, 2 minus charges are there. See second complex I written on the board, see this is actually oxidation number is plus 3, primary valence is 3, secondary valence should be 6, 5 amines are there, 1 chloride I have written in the board, inside the ligand, inside the coordination sphere, then this is the complex. Then type of electrolyte 1:2 and total number of chlorions 2 chlorions precipitated. Charges, once you are saying it is 2 chlorions are there, 2 negative charges and 2 plus charges will be there. Therefore, total charges in this case coming to be what 4. Let me write one more, CO 4NH3. CO 4NH3, I decrease one more amine ligand, 6 amine ligand, 5 and 4. Next, what is the oxidation number again? Cobalt 3 only, primary valency coming to be 3, secondary valence should be 6. How many amines are there? 4 amines. 2 chlorides you have to write inside the bracket. See CO NH3 taken 4 times, Cl2 and Cl. Then type of electrolyte, it is simply 1:1, 1 cation, 1 anion, 1:1 complex is there. Next, how many chlorions are precipitated? Only 1, Cl minus and AgCl. Check it how many charges, 1 minus and 1 plus, 1 minus 1 plus, therefore it is what 2 charges. Here about the charges you should be very careful, 3 plus 3 6, 2 plus 2 4, 1 plus 1 2. Let me write the last complex, CO 3NH3 Cl3, 3NH3 Cl3 in this particular. Now again cobalt oxidation number is 3, primary valence is 3, secondary valence is 6. 3 amines are there, you have to write all the ligands within the bracket, CO taken thrice, Cl3 and all, then it is what a complex. Type of electrolyte, it is zero electrolyte we call. Why? Not producing any type of charges, any type of ions, therefore it is what zero electrolyte. Next, number of chlorions, all are inside, therefore no ionizable chlorion is there, therefore number of chlorions produced will be again 0. And how many charges? Charges also 0. Like this, we can, once you are taking a complex according to Werner theory, you can easily see what type of complex that is, what number of chlorions and what are the charges you can say. I will give few more examples which are based on platinum. These are cobalt complexes. I will show how this particular number of particles and charges for some of the platinum complexes also. I will show to you some platinum complex I will take. Platinum 6NH3 Cl4. Platinum 6NH3 Cl4. Yes, 4 chlorions are there. Platinum oxidation number is 4. In platinum plus 4, I have shown a table that primary valency 4, secondary valence should be 6. Then, how to write the modern formula for this? All the amine ligands you put in within the bracket. Then PT NH3 taken 6 Cl4. This is the complex. Now, type of electrolyte 1:4. Then 1 complex ion and 4 chlorides. Therefore, it is what 1:4 complex. Next, how many chlorides can be precipitated? Here it is what 4 Cl minus. Therefore, 4 AgCl is getting precipitated. Next, how many charges? Once you are saying 4 negative charges, 4 positive charges will be there. Then total number of charges produced will be what 8 charges. 8 charges. Next, to take one more, I am decreasing one amine ligand Pt 5NH3 Cl4 you take 5NH3 Cl4. Again, platinum oxidation number is 4 and primary valence is 4, secondary valence is 6, right? But only 5 amines are there. One of the chloride ligand you have to write inside the bracket PtNH3 taken 5 Cl. 3 chlorides are outside. Then it is what to say? Come on, say 1:3 electrolyte, and the number of chlorides precipitated will be 3 Cl minus in the form of 3 AgCl charges. Here 4 plus 4, 8 you said. Here 3 plus 3, 6 charges. 6 charges. Next, Pt platinum. Let me write 4NH3 Cl4. 4NH3 Cl4. Primary valence is 4. Secondary valence should be 6. 4 amines are there. The 4 amines and 2 chlorides you have to write inside to make it 6. 4 Cl2 and again Cl2. Then it is what 1:2 electrolyte. Yes, it is 1:2. Then number of chlorides 2 Cl minus and 2 AgCl. Number of charges coming to be 4. How the charges? Don't be confused here. 4 plus 4, 8. 3 plus 3, 6. 2 plus 2, 4. 4 charges. Let me take one more Pt 3NH3 Cl4. Again, oxidation number 4. Primary valence is 4. Secondary valence should be 6. Only 3 amines are there. 3 you have to write inside Pt NH3 taken thrice and Cl3. 1 Cl you are writing outside. Then it will be again 1:1. 1:1. We are clearly observing 1:4, 1:3, 1:2 and 1:1. Then number of chlorides, only 1 chloride is there outside. 1 AgCl is getting precipitated. Total charges coming to be 2. The last complex let me show in this Pt and 2NH3 Pt 2NH3 Cl4. Now again oxidation number plus 4, primary valence is 4, secondary valence 6. All the ligands you have to write inside the bracket Pt NH3 taken 2 Cl4. 2 Cl4. Then it is what a type of electrolyte. Therefore, it is what 0 electrolyte. It is not carrying any charge, not ionizing. Therefore, number of chlorides also coming to be 0. Number of charges also 0. Like this, he has actually taken a research of these particular different types of cobalt complexes and platinum complex. Whatever he has actually researched with cobalt and platinum complexes, entire the information we have put in the form of a table for different cobalt complexes and different platinum complexes. Now, let me give 1 or 2 questions which are appeared in the recent exams. How this particular question appear in the exam, how to answer that particular question. Right. See how the question appear in the examination. I am giving one question. Right. Aqueous solution of cobalt trichloride. What it is? Aqueous solution. On reaction with ammonia. On reaction with ammonia. Produced 2 complexes. Produce 2 complexes. Complexes say A and B. 2 complexes A and B. Complex A and B. A gives a precipitate of 1/3 chloride ions. 1/3 chloride ions. A is giving a precipitate of 1/3 chloride ions, and B gives a complex. B gives a complex of 6 charges and 4 particles. 6 charges and 4 particles. What are the AB, chemical formula of AB complexes COCl3 aqueous solution on reaction with ammonia producing two complexes A and B. A gives a precipitate of 1/3 chlorions and B gives a complex of 6 charges and 4 particles. 6 charges and 4 particles. What are the formulae of A and B? This is one of the question recently appeared in one of the entrance exam. Let us consider COCl3 a aqueous solution. This you are treating with what? Ammonia. Yes, you are treating with what? Ammonia. Then you are getting two complexes A and B. Two complexes are produced. Two complexes A and B are produced. Then what is the information of complex A? A gives a precipitate of 1/3 chlorions. How many chlorions are there? 3. Out of 3 chlorions, 1 is precipitated. That is the meaning of what? 1/3. 1/3. Means how many chlorions you write outside the bracket? 1 chlorion you write. Out of 3, 1 is precipitated. Therefore, 1 is outside, 2 are inside. Then how many amines should be there? Total coordination number you have to make it what? 6. Therefore, 4 plus 2 it is what? 6. Then put a complex CO. This is the chemical formula of complex A. This is what actually, this is producing 1/3 chlorions. Out of 3 chlorions, 1 is precipitated. So this is what 1/3 chlorions are precipitated. This is the complex formula A. What is the information for B? Check it. B gives a complex of 6 charges and again 4 particles. 6 charges you have to get. See, getting of 6 charges, 3 chlorions should be outside. 3 chlorions should be outside. Why? 3 minus and 3 plus. Therefore, 6 charges. Next, 6 charges, 4 particles. Yes, 4 particles you can easily say first particle and 3 total particles coming to be 4. Therefore, chlorions, all the chlorions are outside. Then you have to write only amine ligands inside. This was 6. This is what a complex. So, a complex, a COCl3 on reaction with ammonia producing two complexes A and B. A gives 1/3 chlorions precipitate. B gives a system of what? 6 charges and 4 particles. These are the chemical formula of A and B. Chemical formula of A and B. This is the type of questions appearing on Werner's theory. It is easy theory and easy to understand. Therefore, concentrate more on this. Any question you can easily do on this particular Werner's theory.